Good morning, everyone. My name is Devarshi Choudhury. I'm a final year PhD student at the University of Amsterdam. I'm working with Professor Anna Watts as part of the NAST collaboration with some of our other team members. And today I'll present to you our latest results on the nearest and brightest Millisecond Pulsar J0437 that's been analyzed using NICER. Well, I don't need to introduce neutron stars to this crowd, but basically you have these stellar remnants from supernova explosions that are about city-sized in diameter, having 1 to 3 times, let's say, the mass of the sun. And so a natural question that arises is how do these objects sustain themselves under the immense pressure of gravity? What are they composed of? Well, neutron stars aren't just a giant ball of nucleus, but a rather layered structure. You have broadly divided crustal layers and the core layers. The crustal layers consist of, let's say, an ionic lattice, basically nuclei, embedded in a sea of degenerate electrons. But as you go deeper, these electrons merge with protons as it's energetically favorable, and you get increasingly neutron-rich nuclei. And you also start forming nuclear pulsar, which are these elongated forms of nuclei. But so we can simulate how these nuclear pulsar and the crustal layers are like pretty well from first principles. But when we cross the nuclear saturation density in the core, we don't really understand what's going on. There are many possible theories of what kind of state of matter could exist, and we cannot theoretically constrain of what it actually is. You could have typical nuclear matter consisting of neutrons and protons, but in superfluidic or superconducting states. Or you could have more exotic states of matter that you don't see anywhere else in nature just by themselves, say deconfined quarks or strange states of matter like hyperons and so on. And this is something that we want to find out. How do forces of nature interact? What kind of particles exist under such extreme conditions? But how can we do that for such a distant, tiny object? Well, lucky for us, the dense matter physics in the core of the neutron star, what kind of particles it's made of, dictate what's known as the equation of state of a neutron star, which is the relation between pressure, shown on the y-axis, and density on the x-axis. So depending on the composition, you would have a unique equation of state in this equation of state model. Here are just a few examples. It's like a whole family of them. The equation of state, in turn, dictates the mass and radius of a neutron star. So you have a direct one-to-one relation due to POV equations, stellar structure equations. And the mass and radius, in turn, govern how the curvature of the exterior spacetime is like. So as surface emission, which is in the form of X-rays, they traverse this curved spacetime, this information gets encoded in it. So by collecting and analyzing this X-ray data, we can constrain the mass and radius, and trace back all the way and place constraints on the possible core compositions. And in my talk, I'll focus on this part of this plot, getting to the mass and radius from X-rays, for which we use a technique known as pulse profile modeling. And here's a schematic of it. We record X-ray data and information about the instrument used to collect it. We record a neutron star model that can simulate such X-ray data, following which we perform sampling to obtain our parameters of interest. And in our group, we have been developing a software called XPSI, standing for X-ray Pulse Simulation and Inference, the GitHub link of which is available. And so in my talk, I'll take you through each of these aspects, starting with the X-ray data and instrument in the context of Pulsar J0437, one of the main targets for this modeling process. So let's start with the instrument. We are using NICER. It stands for the Neutron Star Interior Composition Explorer. It is this telescope here, which is aboard the International Space Station. NICER has this unique, unique advantage that if there's a hardware issue, sometimes astronauts can go and fix it. In fact, right now there's a micrometeorite damage which has caused a hole in NICER, and astronauts are preparing to go and basically duct tape it. With NICER, so it's an X-ray timing instrument which is highly sensitive in the soft X-ray band and has very high time and energy resolution. This makes it ideal for pulse profile modeling of rotation powered Millisecond pulsars in particular, which are non-accreting sources. So you have no accretion disk, and all of your surface X-ray emission is arising as a consequence of charged particles guided along open field lines, bombarding on the surface and releasing X-rays. This allows for stable hotspot configurations to form on these objects. Now, NICER has already analyzed two sources previously and has published the results. J0437, which was the first source on the left, and 0740 on the right. W30 is quite a bright source. Let me first mention what you're looking at, the plots here. These are the X-ray pulse profiles. So you've got the X-ray counts binned as a function of the rotational phase of the star on the x-axis and energy channels on the y-axis. So W30 was quite a bright source, but it was an isolated system. It had no binary companion. O740, on the other hand, this is a massive pulsar, 2.1 solar masses. We have this information because it has a binary companion. And so from radio timing, you have this priors on the mass and inclination. But it's a much fainter source. You can barely see the pulses in this 2D phase energy result plot. You can see how many less counts it has compared to W30. It's got cut off, it's like 30,000 tons here. And so we have mass radius measurements from these. This we already have mass. This was the first time we got a simultaneous mass and radius measurement when the mass was previously unknown. And now in comes J0437, which is the prime nicer candidate, being the closest and brightest millisecond pulsar. It has far more counts than even J0030. That's 30,000 here, which is like most on the lower end here. It is also in the binary system, again giving us mass constraints, priors, and inclination, and so on. O437 has its own unique challenges, however. This is an excellent Newton field of view image of the pulsar. The pulsar is located here. And the yellow dashed circle represents the nicer point spread function. And the blue circles represent other X-ray sources of contamination for us. And immediately you would notice a particularly bright contaminant, which happens to be an AGN. And so nicer does not actually point directly at this pulsar, but a little offset from it at this position of optimal pointing to maximize the signal to noise ratio. This reduces the number of counts we get, but still it's a very bright object, so it's not too big of a problem. But during analysis, we found that there is still enough contribution that we actually had to go ahead and observe the AGN with nicer in order to get some kind of a background constraint at this position. Okay, with our data in hand, let's take a look at how we can simulate the data. So for the model, being compact objects, we need to account for relativistic effects. We are trying to ray trace X-ray photons all the way from the surface of the neutron star to the as incident on the Space Telescope. And here the animation is showing the effects of light bending. You can see like the star's apparent radius is larger. You can see the two poles at the same time. It affects the waveform in this manner where it sort of gets squished a little. And if you, in certain scenarios, you might just end up omitting the eclipse because of these light bending effects. You also have Doppler boosting, which means that your waveform gets skewed in this fashion as the arriving side gets brighter before where it would normally be. And to capture these effects, we use a space-time model consisting of an oblate Schwarzschild plus Doppler approximation because it can closely mimic the exact solutions without being nearly as computationally expensive. Now, as mentioned before, O437 has radio priors, so particularly the mass prior is very important for us. It can really help tighten the radius measurement, and these affect our ray tracing aspects. We have very tight Gaussian priors on these three parameters from the Parkes pulsar timing array. And to place particularly the mass prior into context, here is a mass versus radius plot of the previously inferred nicer sources, the O740 and W30. To remind you, W30, bright source, no binary companion, so you could only constrain the mass and radius. We could get a decent handle of it. But for O740, we had this very beautiful radio mass measurement from all these lovely radio colleagues, and so we could get a much better grip on the radius. O437 combines the best of both worlds, right in W30, a much tighter radio mass prior than O740. We also need to model where these surface X-rays come from, and we don't really have a very good understanding of how they might look like. There have been simulations for of pulsar emission mechanisms for millisecond pulsars, and we base phenomenological models inspired by these models. We start off with, say, a simple dipolar configuration like this, where you have like a circular single temperature hotspot. We then introduce complexity, let's say, in the form of two temperature regions. We can have masking elements to create rings, have them protrude to have presence, and we play with a combination of these things, see what fits the data best. Okay, with data and model in hand, we perform sampling, for which we use the nested sampling software called Multinest, because we expect a rather multimodal posterior parameter space, and we want to compare evidences to best select our models. We're also improving this. We are now implementing UltraNest and playing with like simulation-based inference to cross-validate our current results and also get more robust constraints. But for now, for this work, we use multinest. And so without further ado, let's take a look at the parameters that we got, starting with the surface map for this neutron star. So here I'm showing you the maximum likelihood solution for our best fitting model, which consists of a ring and a 2-temperature spot. The ring is located in the northern hemisphere, the northern pole, and the 2-temperature spot is in the southern hemisphere. This is as viewed from the equator, and this is as viewed from the observer inclination angle. And such a configuration implies the presence of some kind of an offset dipolar or quadrudipolar magnetic field line structure. And we additionally find that the canonical centered dipole that you see in your textbooks simply cannot explain our data. We end up with horrible residuals in this case. And this is consistent with the radio observations for this source, which also require the presence of multipolar moments to explain the radiomorphology. Now on to mass and radius. Here's the posterior distribution for the mass and radius, the 1D and 2D paired intervals. And for the radius, you get a median value of 11.36 kilometers, plus 0.95 minus 0.63 kilometers, which is some of the tightest neutron star radius constraint with an uncertainty level of plus minus 7%. And the mass is pretty consistent with the radio here, the dashed dotted lines of the priors, and you can see it very strongly overlaps, which is not a surprise. Again, to place this into context, the previous NICE sources are shown here. This was the mass prior that I showed. And this is where O437 stacks up. And you can see it's much tighter than even the previous results. And this is consistent with gravitational wave observations of merging neutron stars, where they get tidal deformability measurements. And for 170817, Abbott et al. Found using equation of state independent relations, similar radii for similar mass ranges. So we make our gravitational wave people happy. We additionally find for their follow-up study of equation of state inference using all of these NICE data, along with gravitational wave data and new priors on the chiral effective field theory, to further constrain what the radius of a 1.4 solar mass neutron star should be like, assuming certain equation of state dependence. And with that, I would like to summarize my talk. We studied O437, got some of the tightest neutron star radius measurements, which prefer software equation of states consistent with gravitational wave observations, and got a surface map which implies the presence of offset dipolar or quadrudipolar magnetic fields. Thank you. Any questions?
Thank you. I should have time for a couple of questions, Paulo.
No, there is beaming indeed. So here I quickly glossed over it. So we use this atmosphere model called NSX. And in this case, we have only used a fully ionized hydrogen model. Typically, we expect hydrogen to be the most likely candidate because of settling of the elements over time. But in the future, we also, like for other sources, we have also tried playing with helium and carbon atmospheres. And for example, maybe I can show this one. Yeah, so O740 we have already analyzed with hydrogen and helium, but because of its mass prior, in this case, it doesn't really move around much, the mass and radius. But for W30, it does make a bit of a difference. So we are hoping that that also turns out to be the case for O437, where the mass radius is pretty constant despite the atmosphere choice. That's an excellent question. Absolutely, we would. And that's something that we are hoping to work on. So to answer your second question first, so if you have a magnetospheric model, that would help us get a much better understanding of the surface emission map. Because right now we are trying to fit, well, physically inspired models, but phenomenological ones to see what suits best. But there was a follow-up on, so let me show this plot again. Yeah. So for W30, there was a follow-up study where they used magnetospheric models to fit both NICE findings and I think Fermi findings of gamma ray emission for this pulsar, and they were able to rule out certain models which were still competitive for us compared to our headline result. So that would indeed be better, and that's something we are trying. As for emissions from beyond the surface, so we don't have an accretion disk in this case, so any kind of things that's a bit too far from the surface won't really be It won't really require relativistic ray tracing, and it should not be, in principle, locked with the rotation of the star, and therefore it would not be, like as we phase resolve or phase sum, the things shouldn't coherently add up. Of course, you might have these thermal power law tails from higher X-ray components, but in our cases, we haven't really seen any kind of, well, much of a contribution in the soft X-ray band, so we are less sensitive to that. And any other thing that, any other background emission that we do have a background model which tries to marginalize over what's the best fitting background. That's how we try to account for it.
Actually, we are out of time, but you can continue asking questions in the query or in the coffee break that we have now until 11 p.m. 11 a.m., sorry. So